Okay, people, so here is some selected questions I'm going over for practice review test number 1. Make sure you're looking at the right one, or else we off. Alright, so when you get questions like this, make sure you draw a picture. So you're like third class lever, okay, F-R-E. Third class lever, the effort's in the middle. That means the fulcrum's on one end, the effort's in the middle, and the resistance is on the other end. Okay, so when it says, I'd like to draw a picture before I even read the rest of the question. The distance from the effort to the fulcrum is blank compared from the resistance to the fulcrum. And if it's a third class lever, that's got to be smaller because the effort couldn't be in the middle. It can't even be equal to, or it wouldn't be a third class lever, so it has to be strictly less than. So draw a picture on it. All right, same deal on this one. If you draw it out, you'll be able to get an answer, right? Second class is when the resistance is in the middle. And then you can read it and get it. I did want to talk about number 3 also, because usually I say you don't count the string you're holding on to, except really long arms. Except if you're doing this, if you're lifting the same direction the weight's going, you count both of them. So it actually would be 2. If you were lifting the opposite way, you wouldn't count the one you were holding on to. Okay, so, we can look at notes for those, that kind of thing. Let's keep on going. This is an old question from one of our first guided notes that you've probably forgotten by now, but work equals force times distance traveled. That's what work is. Okay, work is force times distance. It's been a while. Let's see. We're going to do a problem just like 11 later on, so with a second class lever, I didn't want to overdo that. All right, so let's get to a couple of these. So what is the weight or resistance you could lift using a first class lever if you apply 20 pounds of effort? The effort arm distance is 10 feet and resistance is 5. So here's 5 feet. This is dr, because that's resistance arm distance. And the effort, dE, is going to be 10 feet. Okay, so first thing, before I can answer about how much weight I could lift that's going to compare to that, I have to use what I got. And what I have is dr and dE. So that should remind you about IMA. So when it's with distances, use IMA. I'm a deer. Right? See how I write the formula still? And then IMA is going to be dE, which is 10 over 5 feet and feet. Don't forget your units, but they cancel out. You get an IMA of 2. And then, so ideally, how can I lift 20 pounds of effort force? Well, forces go with AMA. And AMA free, FR over FE. This is your effort force. So I'm going to put a 20 down here. I also get to use my answer from here in AMA. So you're going to say 2 equals FR over 20 pounds. And then since the thing I care about is in the top, it's an easy problem. I don't have to do the old switcheroo. Those cancel and your FR is 40 pounds. So there's my winner. Okay. Similar, thought we'd do a wheel and axle because it's been a while. Find the mechanical advantage of a wheel and axle if the wheel has a radius of 1.5 feet. Okay, it's important that you know that's a radius. And then the axle has a radius of 6 inches. So there's 2 sneaky things in here. And one is it matters where your effort is. So this must be like a car driving where the effort's on the axle and the resistance will be the road. Okay, unlike a spigot or something like that. So it matters here. So if you're going to find the mechanical advantage, and I have distances, I'm talking about IMAs. So I'm a deer, and this is where you're going to get yourself in trouble if you are not someone who writes units regularly. Because if you're not paying attention, you might be like, oh, my force effort is 6 over 1.5, right? There's my resistance and my effort. Since they're both talking about radii, I don't have to worry about comparing unlike things. If you just wrote the numbers, you're getting this problem wrong, I promise. If you actually took the time to write the units, you're like, wait a second. This is 6 inches, and that's 1.5 feet. I either have to turn them both into inches or both into feet. So that's up to you. I'm going to go both inches. 1.5 feet, well, 1 foot is 12 inches. 1.5 feet is 18 inches. So if I do that, now my units cancel. You have 6 over 18, which is 1/3, also known as 0.333. So there you go. If you would have done it the other way without units, you probably would have said 3, and you would have been wrong. So I know I always harp on how important units are. Here's an example of why. All right, so and then I wanted to do, I think, one more at the back. Yeah, this extended response problem. A wheelbarrow is used to lift a 150-pound load. So let's draw it real quick. Wheelbarrow, 150 pounds. That's your force resistance. Okay. It says from wheel and axle to center of the load. This is a second-class lever, by the way. Wheelbarrow is a classic example. The length from the wheel and axle to the center of the load, that's your dr. So that's why I label these things. Force of resistance is that. Distance of resistance. And then length of wheel and axle to the other one, this is distance effort, is 6.0 feet. And this one was 2.0 feet. Okay. So if I'm asked IMA, I'm a deer, that's going to be DE is 6.0 feet. I always write my units, we just saw why. Over 2.0 feet. Units cancel and you get 3. So your IMA is 3. Use static equilibrium, calculate the effort force needed to overcome the resistance. So how much effort do I have to put in to overcome this 150 pounds? Well, you can use your AMA formula, and equilibrium means we're pretending friction doesn't exist. And I'm going to put AMA free, right? And F, and I'm going to put in my answer from IMA in for AMA, because that's what static equilibrium means. We get to pretend friction isn't a thing, and FR is 150. I'm glad I did one of these, because when the thing you care about is in the bottom, you do the old Western switcheroo with the other side. So FE is 150 pounds over 3. So that's 50 pounds. Okay, so I'm glad I showed you one with the resistance distance. And then I just drew some pictures here. Hopefully you can look at that and think about them. We got a shovel, your hand at the back is your fulcrum, your hand in the middle is your effort, and then your flinging dirt, which is resistance. And scissors, the fulcrum's in the middle. Tweezers we did in class, you squeeze in the middle, so that's the effort. And I always go with what's in the middle. So here, wheelbarrow is a clear second-class lever. Stapler I hadn't thought about, but a stapler is pretty similar to tweezers, where, well, let me think. Yeah, it's a tough call, but I think when you push on a stapler, it sort of depends where you push. But I think my effort's in here, and the stapler comes down the outside. Like the staples your resistance. That one's questionable. And then a broom is another thing, like a shovel. Hole punch was a new one. I didn't think about that. It's kind of like a nutcracker where the resistance is in the middle. And a hammer, first class lever, because when you're removing a nail, the hammer's the fulcrum, the nail's the resistance, and your effort is like pulling it this way. So I'm pulling down, it's rotating on here, popping the nail. All right. Anyway, so that's a quick video on that, and I'll make another little one on the other one.